we've really cheated. We've imagined the existence of this oracle. That's totally out of the spirit of RL. I mean, this just doesn't happen in practice. You know, the whole point of reinforcement learning is there's no supervisor to tell us, hey, the right answer was 7.3. We need to figure that out directly from experience. So how do we do that? What's the method we use? Well, we're going to use the same fundamental methods that we've seen in the last two lectures. We're going to use Monte Carlo and temporal difference learning methods to give us a target to use for our function approximator instead of the oracle. So far we basically assumed that we were given this v pi of s. But we know that we've seen in the previous lectures that we can get some targets that estimate v pi of s directly from experience. How do we do that? Well, if we use Monte Carlo learning, then this target will just be the return. So we use the return as an unbiased estimator of v pi. And so the idea is that if we substitute in, now we're just going to do this by substitution. So think of this as like copy and paste exercise, in that we've developed an algorithm for supervised learning, and now what we're going to do is wherever we saw v pi before, we're going to copy and paste some other target instead that we arrive at through a reinforcement learning method. So the first thing which we're going to paste in is the return. So we're going to basically take the return here, and what this algorithm says is, the change to our feature vector, or to our weights, the change to our weights is we're going to move a little bit in the direction of the error between the actual return. So, I'm now going to say, I'm going to start here, I'm going to estimate using my function approximator. I'm going to come up with some estimate that says I'm going to get 10 units of reward. And then I'm going to see what happens, run my entire trajectory out, discover that I actually get 12 units of reward, generate an error of 2 units of reward, and update my weights a little bit in the direction of that error multiplied by the gradient of my function approximator that tells me how to move in the direction that changes that, to change my values. So that's how to plug in Monte Carlo. We basically take our supervised targets, our v pi's, and we replace them with a return. So now we're just updating things. We're fitting our value function towards the returns. The returns become the supervisor. So we're kind of doing supervised learning on the returns. Is that clear? If we use TD learning, we're going to use a different target as our estimate of v pi. We can use our bootstrap estimate. We can use the TD target. So now we're basically going to say, instead of waiting all the way until the end of the episode and getting some estimate of the return, I'm going to use the TD target. I'm going to start in some state. I'm going to estimate that I'm going to get 10 units of reward on this trajectory. Then I'm going to take a step, see that I get, say, 1 unit of reward, and then estimate that I'm going to get 8 more units of reward. And so I'm going to say, okay, well, my TD target will be the 1 plus 8. So I think I'm going to get 9 more units of reward. And now we're just going to do, just like supervised learning again, we're going to treat that as our target and adjust our function approximator so as to fit these values that we're predicting. So now we're going to use that as a training sample. We're going to try and fit our function approximator towards that example where we think we're going to get 9 units of reward. So we do that again by moving a little bit in the direction of the error between our 9 units of reward and our 10 that we predicted before, multiplied by the gradient that helps us achieve that, to realize that change. We can do the same thing with TD lambda. I won't go into the details of TD lambda today. You can look at the previous lectures. Same idea, we use the lambda return. So this is the thing which sort of interpolates between TD0 and Monte Carlo learning. Whatever our lambda return is, we treat that as the target, and we fit those lambda returns that we see. We use those as the targets for our function approximator. So what's this look like? So we can think of this as a process that looks a lot like supervised learning. So when we do Monte Carlo learning, we're basically going to use the return, and we're going to build some training data. Think of this as building training data, but we're doing this kind of incrementally. Like we first of all see state S1, and we run a trajectory from it, and we see that we got a return of G1. And then we visited state S2, and from S2 we got a return of G2, all the way up to our final state, our trajectory or our, wherever the agent got to, and its final return here. So that's the data that the agent's seeing. It's seeing this data, it's seeing all of these states, and from each of those states we've got some estimate of the return, which we're using from our Monte Carlo learning. Okay, so our Monte Carlo, we're just rolling out and seeing how much reward we actually got from each of those states. Think of that as like your training data. And so now, what we're going to do is basically, just like supervised learning, we're going to treat this as a data set, and we're basically going to adjust our function approximator so as to fit the g's and estimate what the g's will be from any one of these s's. So this is just like supervised learning. And the simplest case is using linear Monte Carlo policy evaluation. So this is the same as the last slide, but now all we're going to do is substitute in our linear function approximation, so the gradient just becomes the feature vector, and all we do is we plug in the return, so we adjust the weights of our linear combination a little bit in the direction that corrects our estimated value towards the return. And we know that this has to work because we're just doing stochastic gradient descent. Stochastic gradient descent converges to an optimum, and we know that Monte Carlo learning gives us an unbiased estimator of the true target. So essentially it's as close as you can get to an oracle. It's just a noisy oracle. And so this will work, it just may be a little bit slow. So even if we use nonlinear value function approximation, Monte Carlo will converge to some local optimum, or in the linear case, it will find the global optimum. We can do the same idea with TD learning, but now we've got this bias sample. So we don't have the true oracle anymore, we don't even have a noisy oracle, we just have some biased estimator of the target. So, you know, what I think will happen after one step, and then invoking my own function approximator again. So, you know, I get the reward, RT plus 1, and then I have to query my own function approximator to estimate how much reward I'm going to get for the rest of the trajectory. That's how we get the TD target. So this thing is biased because we're having to go through our own neural network or our own linear function approximation to figure out what these values will be. And so this gives us a biased sample of the true value. But we can still, once we've accepted that we've introduced a bit of bias, we can do the same idea. We can create this data set. What's the data set look like now? Well, it's like for each state, we have a TD target. So it's like I was in this state, and I saw one step of reward, and then a value function estimating how much reward I was going to get from that point onwards. Then I was in another state, and I got one step of reward plus the value function after that. And I can build up a whole data set that basically uses these TD targets as like training data. We start to fit our value function towards these TD targets. So let's do the simplest case again. Let's consider linear function approximation. So now what we're going to do is plug in our TD target. So we're going to basically say we're going to adjust our weights a little bit in the direction of the error between what I thought the value was going to be and my one-step estimate of the value, the TD target, like, you know, after one step, how much do I think I'm going to get? Treat that as the target. We're going to see that there's some error. Like if you're playing a game, this could be the thing that says, you know, before I played the move, I thought I was winning, and then I played my move. It's like, oh no, I actually just saw that I blundered, and I'm going to, you know, lose my queen. And so that generates an error between what you thought was going to happen and what actually happened. We use that error signal to correct where you started. Now you think, oh, I was actually losing all along. I just hadn't realized it until I took that step. And now this gradient tells you how to adjust your function approximator to make it more like you thought you were losing in the first place. And so we can compactly write that in the following way. We update our parameter vector, step size multiplied by TD error multiplied by feature vector, or the gradient in the more general case. Feature vector in the linear case, gradient in the non-linear case. Good question. I've been quite suspicious that you're all so quiet. It's like you're normally like asking questions every 5 seconds. Good.
So you're saying that you generate this data set, and then you're doing like supervised learning on the data that you generated. So if you do this after every step, or is it after the end of the
Yeah, great question. So I'm just actually trying to give a flavor of how this relates to supervised learning, so you can think of what it means to train this function approximator. In practice, we're doing everything incrementally. This is the first half of today's class. Incremental, online updates. So every single step, we're going to take a step, we're going to see, we're going to generate our TD target. So like so I'm in this state, I thought I was going to get some value, I take my step, I get some new estimate of the value, I generate a TD error, I update my weights immediately, and then I move on to the next step. So the data set idea we'll come back to later when we do batch methods, but it's just to see that there's a relationship between this and supervised learning, that we're doing something where we're associating for each state, we're associating each state to some target. And we're just playing with what that target is. We're playing with whether that target's the, an oracle, whether it's the Monte Carlo target, whether it's the TD target, or whether it's like a TD lambda, a lambda return. Okay, and even though this is biased, it's really important to note that there's a famous result by Tsitsikas and Van Roy that shows that linear temporal difference learning still converges if you use linear function approximation. Despite the fact that we've introduced this bias, it still converges close to the global optimum, where close depends on things like your discount factor. And then finally, I won't dwell on this, we can do the same idea with TD lambda. And now the data set, if you like, the data that we're generating, again, we're still doing this online, but the association that we're making is each state we're associating with some lambda return now. So the lambda return is this mixture of all your n-step returns. And so we're going to try and basically learn to make our value function fit it to these lambda returns. We want to take some weighted combination, lambda weighted combination of what I think is going to happen after one step, after two steps, all the way up to infinite steps, and then make our weighted combination of all of those estimates, call that our lambda return, and then fit our value function at each of these states towards those targets. And we're going to do this incrementally, step by step, but conceptually there is this data set that we're kind of moving through. And so we can do that either using the forward view. So the forward view has this flavor where we move a little bit in the direction of the lambda return, the error between the lambda return and what we thought the value was going to be, multiplied by the gradient in the nonlinear case, or the feature vector in the linear case. And there's an equivalence, again, just as we saw in previous classes, there's an equivalence to this backward view, where you can use eligibility traces and you can make something which is now truly, we want to achieve online updates, where you take a step, you update. And you can do that using eligibility traces. So briefly, what do the eligibility traces look like? I think someone asked in a previous class, what's the size of these eligibility traces? And when you use function approximation, the eligibility traces are eligibilities now like on the features or on the weights of your parameter vector. They're the size of your parameters of your function approximator. They're not the size of the state space. So the eligibility basically says, look, each time you take a step, we're going to decay our eligibility a little bit, but then increase it in the direction of all the features that you've seen. So this is kind of remembering all the features that you've seen so far according to their magnitude. So the eligibility trace is kind of accumulating credit for the things that happen most and the things that happen recently, and then it decays over time again. So kind of each step we add on, hey, this feature was on, I had a queen at this step, and I had 7 pawns, so those are the things which contribute at this step. Maybe at the next step I only have 7 pawns, those would be the features that contribute there. And you kind of take the sum of all the things which are on and active, or the large features, and they kind of get, the more something occurs in your eligibility, the higher your eligibility is pushed, and that feature will then get updated the most when you actually see an error. And then the TD error is generated in the usual way, and we update our weights now a little bit in the direction of the TD error multiplied by this eligibility vector. So we update our weights proportional to the TD error and how much each of those weights is to blame for the error that we've seen. And without going into the details, again there's an equivalence where if you do this at the end of the episode, if you were to just gather up all your changes until the end of the episode, you would find that you make the same updates forward and backward. These things are equivalent. Right. So just before we do control, is everyone good so far? This is like the main point of this class is these last few slides. And if you're lost, you should ask now, because it's just going to get, we're going to build on it and do more things. Yeah.
So G lambda and the target of these slides depends on the value function.
Yes.
So why don't we have a term for that dependence in the update?
Okay, great question. So the question was, why does the gradient only depend on our predicted value function? Let's go back to the simplest case with TD0, and because we can still ask that question already here. So the question is, when we take the gradient, why don't we take the gradient of both the target and our function approximation? Why is the gradient only of our function approximator? The answer is, it's a slightly tricky answer, okay? One way to answer this is to say, we're doing TD. TD means that you kind of, you're always pushing things towards what happens later because you trust the thing which happens later. You don't want to reverse the flow of time. You don't want to update the estimate of where you end up later towards what happened before. Like if you have the gradient of both of these things, it's like you've kind of got a spring and you're pulling your value function of what happened afterwards towards the value function of what happened before. You're pulling them all together to try and reduce the error. And you can show, there's a very simple example where you can show, even in a table lookup situation with a stochastic MDP, if you do that, you will get the wrong answer. You will not find the correct value function. And the reason is that this trying to minimize for this error in this way doesn't, you need the flow of information to be grounded. You need to ground things, and the way you ground things is to go later in time. Like as you go later and later in time, you see more and more real rewards. And the more real rewards you see, the more you can trust what you've seen in terms of what's actually happened. You don't want to reverse the flow of time and update something where you saw a real reward towards something where you hadn't seen that reward yet. You will kind of get the wrong answer if you do that. And so putting the gradient on both terms is doing a little bit of that time reversal. It's doing both the forward and the backward direction. And there are variants of that which are not quite so bad as the way I've made it seem. The family of methods is called residual gradient methods. And so it's a well-known idea. People do this in practice, but it's also well known that if you just naively plug in the gradient here of this term as well, so if you just had the gradient of the error between these guys, you would get the wrong answer. You have to be a bit clever about taking expectations, and then that algorithm isn't actually practical, and you can't do it in incremental settings because you need 2 samples. And this version works well in practice, and you just need to be careful. It's intuitively, it's appealing when you first think about it to do what you suggest, but I would recommend against doing that unless you really know what you're doing. But there are cases where it's a reasonable thing. Okay. I'll come back to a related question in a minute, but thank you, that was a great question. Okay, let's move on to control. So we're going to use the same idea for control that we saw in the last lecture, where we're going to still build on our idea of generalized policy iteration, but now we're going to use approximate policy evaluation. So what we're going to do is we're going to start off with some parameter vector now, and we're going to say, okay, that parameter vector, that's going to define some value function. And what we're going to do is basically act greedily with a little bit of epsilon exploration, for example, with respect to that value function that we've defined. So this might be our neural network. We act greedily with respect to our neural network. That gives us a new policy. And now we want to evaluate that new policy, so we run some more data, we update the parameters of our neural network. That gives us a new value function. And now that new value function, we can act greedily with respect to that, and so forth. And again, just like in the last lecture, we're not going to go all the way to the top here. We're not going to waste millions of samples of experience trying to exactly fit our function approximator. Indeed, we know that if we're using a function approximator, we're not going to precisely be able to achieve equality here ever anyway. So what we're going to do instead is take some steps towards it, and then immediately update our policy. And in the most incremental case, where we just do TD for one step, we're going to do this every single step. Every single step, we're going to start evaluating our policy. We're going to update our neural network once, slightly adjust the shape of our curve, and immediately act with respect to that latest neural network to pick our actions. So there's no reason to wait until you've really adjusted your neural network an awful lot before you start picking actions again. You know, why not always use the freshest, most interesting information you've seen? And so that's the idea of this approach here. and we'll see some variants later, but you can do policy evaluation, where you do approximate policy evaluation. So again, we're trying to estimate the action value function now. So let's just back up. Like last class, we saw that there were two ideas. In order to do control, we needed to take generalized policy iteration, and add two new ingredients, where we needed to use the action value function Q, so that we could be model free and still be able to pick the greedy action. And we needed to have some kind of exploration, for example, using epsilon greedy. Those were the two ingredients that we introduced last week. And so we're going to use those same two ingredients, but now we're going to use our function approximator to get an approximate Q value. So think of this now like a neural network representing Q. We're just going to figure out the parameters of that neural network as best we can, then act greedily with respect to it, throw in some noise to get some exploration, continue our algorithm. So what happens? Does this really find the right answer? Does this get to Q star? Well, of course not, because it might not even be possible to represent Q star anymore. We've used some approximation, so we should expect, in the best possible case, is that we will have some controlled algorithm which gets closer and closer and closer to Q star. But it turns out even that is too much to hope for in the control case. We typically end up with algorithms which sort of oscillate around, and sometimes they get a little bit further before they come back in again. And there's some ball within which they oscillate, and they can kind of come in and out. But in practice, they tend to get very close to the right answer, and so all is well, roughly. So, the first ingredient is we need to do all the same things using Q instead of V. Okay, we need to think of how do we do this with an action value function. So let's just back up. We'll do the same steps again using Q, just to make sure it's all embedded nicely. So we're going to approximate the action value function. So now for any state and any action, we're going to build a function that predicts, with these parameters W, that predicts how much reward we expect to get from that state and action onwards. And then we're going to minimize the mean squared error now between our Q values and the true Q values for our policy. And so we build up our mean squared error. This is the expectation under our policy. So that, with respect to the states that we'll see if we just follow our policy and the actions that we see, we're going to look at the squared error and expectation, and we do stochastic gradient descent again. So just the chain rule, we have our error multiplied by the gradient. And so now what we're doing is we're moving a little bit in the direction of the error between the Q value that I estimated before and the Q value that my oracle gives me, if we have an oracle, multiplied by the gradient. And now, what does our function approximator look like? Well, let's consider the simplest case again. Using linear function approximation, we can now build features of both the state and action. So this might be, we might have one feature saying, how far am I away from this wall if I'm moving forwards? That might be one feature. And I might have another feature that says, how far am I away from this wall if I'm moving backwards? These are like functions of both the state and action which I take. And there's just going to be some number telling us each of these cases. And maybe it's just 0 if I'm not doing the action which I was interested in. Or maybe we generalize across actions. And so that's going to give us features, a feature vector, that tells us about the whole state action space. And so we can build up a picture of what this whole combined state and action space looks like, or what's the value of all of these things. And the way we do that, the simplest way, is by building a linear combination of features. We could also do something more sophisticated like a neural network. And then just follow the gradient. So the gradient update now collapses to change the weights, the direction, the step size multiplied by the error, multiplied by just the features, whichever features are on. So this would basically, in the example I gave, if I actually go forwards, then we would only update the feature corresponding to my forward action, because the other one would have a 0 value. Okay, we can plug in the same idea. So this is just the same machinery again. I'm not going to dwell on it for too long, where we can basically do exactly the same things with Q. We can use Monte Carlo learning. So now, if there's no oracle, what do we do? Well, again, we can use the return as a noisy, unbiased estimate of the oracle. We can use the one-step TD target, or we can use the lambda return, or we can do the backward view TD lambda. to use eligibility traces. So all of these are just as before, but now we're using Q rather than V. And the reason to use Q rather than V is so we can do control. Once we have Q, we can just pick the max over our actions. We don't need a model. We can figure out what the next action we should take is, and continue to do our policy improvement steps. Okay, let's do an example. There's been a lot of slides without getting concrete. So this is probably the most widely used example in all of reinforcement learning. So if you were to pick up like a random paper on reinforcement learning, there's a very good chance it would have this mounting car problem in it. I'm kind of sick of seeing it now, so but you know, it's still, I think it's a good problem and it's interesting to think about. The idea is you've got this car here, it's stuck in this dip, and you can see it's kind of steep here, so how are you going to get out of this dip? The assumption is that your car isn't powerful enough to just drive straight to its goal here. So what it has to do is has to kind of just let go and roll backwards, drive forwards, roll backwards, drive forwards again, and build up enough momentum to actually be able to reach the goal there. And then the question is, well, how do you figure out that control strategy? How do you just do this, not saying anything about the MDP, about the dynamics, you know, do this all model free, we want to solve this. And now we want to do this using function approximation. So what's the state space in this problem? Well, the state space is the position of this car in this continuous state space, and it's also got some velocity, and so you can think of this as a two-dimensional state space, position in one axis and velocity in the other axis. And so the value function looks something like this, where you've got some surface saying for each situation this car might be in, like if it's here and going downhill at some particular velocity, you might find yourself, you know, at some point on this diagram and you want to know, well, how good is that? How much reward will you get? And of course, like usual, how much reward you'll get depends on the policy you're following. So to begin with, if you're just acting randomly, then the value function looks something like this. And so over time, what we see is that as the policy starts to improve, we start to see more and more shape emerging out of this function approximator. This is doing our generalized policy improvement using the SARSA algorithm. Okay, so SARSA, if you remember, it's literally the extreme case of this diagram here. It's the extreme case of this diagram where every single step we update our value function, in this case using a linear function approximator to estimate Q. Every single step we update Q, and every single step we act greedily with respect to Q to pick our next action, but we also flip a coin to see if we do something random to make sure we explore. That's SARSA. That's all it does. And the way that we update Q is using the one-step TD returns, so these guys here. So what's happening is we're on our mounting car, where, you know, in some situation, we have some prediction of what Q is going to be for the action. So we take some action, like trying to apply some acceleration. We've got some prediction of how much value we're going to get. Then we see that we actually end up falling backwards, back down the hill a bit. We see how much Q we now predict in our new state and the new action we will take from there. We adjust our function approximator towards that new Q value. So we think that where I was before and applying an acceleration, that the value should be adjusted, the value of this curve should be adjusted a little bit in the direction of those Q values. And what that does is it's effectively pulling up or down this function approximator in the direction of what we now think the value should be. So every single step you see, you're kind of pulling up or pushing down this function approximator, the shape of this curve, the shape of this surface. And you know, if you took a step and ended up in some situation where you think you're actually doing much better now, you suddenly reach the goal, you know, that will pull up the whole shape of this function approximator. And this particular function approximator that's used for this example is what's called a coarse code, which is like basically lots of overlapping tiles of different shapes and sizes, and they all overlap, and anything which is actually active, which is on, will be pushed up when a particular state is visited. So you visit a state, you think, aha, the features which are on are all the ones nearby this, they all get pulled up, none of the other ones get affected, and you get generalization around the region of the tiles which are sort of active at that point in time. Okay, so that very simple function approximator is sufficient to express quite a complicated shape in the value function. And you see that there's these curves and complicated surface starts to emerge here, and you get these spiral patterns appearing until eventually you end up with something which looks like this. So this is actually using a different type of function approximator, a radial basis function approximator. You end up with this kind of spiral pattern in the position of velocity space. This is a really old figure, you can tell it's got handwriting on it. Wow. And you get this shape appearing, and this is an approximation of the optimal value function for mounting car. And so nothing is exact, like we're generalizing. We don't precisely know what happens for some point in between these things. This is a smooth function approximator that's interpolating within its tiles and estimating some of these values. But you can see that it works very well at getting this space, and this also scales up to much more complicated problems as well. Okay, does that give a bit more of a flavor of what's going on? Good question.
So in this example, you have a continuous state space and a continuous action space.
In this example, good question, sorry. In this example,